Welcome in. So we're going to dive into cubic functions now, and then taking limits of a cubic function and finding epsilon delta proofs for them. So basically trying to find a delta for a given epsilon. So you can see here, we'll share actually all the simulations that I do on Desmos. I'll put it up in the description so that you can take a look and play around. Now, our goal is not just to make it visual, but also just to go through the whole process of understanding how do you find the delta for a given epsilon. So we're going to take a look at several functions, okay, which are going to be cubic, and they're going to be some easier and some harder ones, and then generalize the entire case. Now, if you're interested, I have done this series of videos for the definition of the epsilon delta, put up a link up above there. I have done also the linear case, okay, so for just linear functions, so basically lines, which is a good starting point for finding deltas and what the process is. I'll put up a link up above there. And then I've also done the quadratic case, and you'll see the quadratic case as well. I can put up a link, so you'll see those if you wanted to. And this is now a creation of the series and a continuation. So here are the limits that we're going to be working with, and we're going to be trying to find a delta for a given epsilon. Now, the overall idea behind finding that follows this process, which I have utilized. So the first thing is, when you're doing your proof, you have to find a delta for a given epsilon, and you also have to state that for your profs so that they know exactly what you're doing. And then you're going to be making a connection between the function and the limit, and then the actual small little kind of interval between x minus a, where delta, okay, is actually restricting it. So we're going to be establishing a delta. And then once you're done that, you have to find if that delta that you have found out works, right? So those are the actual steps that we're going to be doing. Now, the hardest step is actually establishing the delta itself, which is my interest in this video, to show you as the students, okay, kind of learning this process. What is it that you're looking for when sometimes it's not the easiest cases to deal with? And these ones are certainly not the easiest ones, but they're not difficult once you grasp the concept. And I hope that you get kind of the eureka moment where you're like, okay, you know what? I think I get this whole concept and idea whenever I'm dealing with linear, quadratic, cubic, and then even further on. So basically any polynomial that someone throws at you. So let's take a look here. We're going to start off with this first example. So that's our step one, right? We want to be able to find the delta for a given epsilon, and you have to let somebody know that you're doing that. Now we want to be able to find our connection. So what is our connection? So now what we can say is, all right, so note, and we're going to write out, so our standardized, so this is going to be x cubed minus x, so that's our function right there, minus the actual limit, which in this case it's 0. So that's what we have there. And now our goal ultimately is to do something like this. So less than or equal to is to find the connection between x and then whatever x is approaching. So in this case, it's approaching 1. And then we want to find some constant in here. So you can, whatever you define that constant, that will be. So let's try to see if we can find a constant. Because when we find the constant, then we can certainly find out what the delta is. All right, so let's start off and break this thing down. So because of this 0, so this isn't actually very difficult for me to go through. So what you will notice is I can factor this out. Remember, I'm trying to look for x minus 1, but I actually right away can see that I can factor out the x. So I'm going to get x, and this is going to be x squared minus 1. So this is going to be exactly the same thing. So the one above is equal to this, right? So that's what we want to be able to see. And then from here, you have a difference of squares. And the difference of squares indeed is going to take out this factor, x minus 1. So you're going to have x, and you're going to have an x plus 1. And you're also going to have an x minus 1 right there. So this is still all within the absolute values, and they're all still equal. Now, when you're taking this thing out, which is exactly what you want to do, and the next step is you want to be able to now create a bound, okay? So you have some kind of a bound C that this is kind of restricting you by, right? So this is what we want to be able to do. So let's try to break this down a little bit further. So what we want is this. We want this thing, and actually I'll just put x squared plus x in here, in that way, and then I'll put outside x minus 1 right here, and we want to be able to put a bound on this. Okay, so what in the world is that bound? So if you've seen the series that I have been developing on these epsilon deltas, you notice that if you don't bound x, right, so as within your kind of domain, initial domain, then you're going to have a very hard time finding, okay, the actual C, okay, so the bound on its own, because there will be no bound if x is unbounded. So if x is unbounded, actually that term will go to infinity. So you do have to restrict it, and we typically will restrict under math. So our goal is to restrict under, okay, so whatever it is that we're approaching. So notice that we have x, okay, is approaching 1. And now what we're going to say is, all right, so let's restrict our x. Let's not make it infinite, but we're going to be working within some kind of a domain. And that domain is going to be related to our x minus 1. So this is kind of like coming in from our delta. But we're going to say, all right, well, let's just restrict it that we're going to be living, okay, within less than 1. It could be less than 2. It could be even 0.5. Okay, it could be 0.25. It doesn't matter what you put in here. But we most of the time, in terms of mathematics, we'll just do something simple. So we'll just kind of bound it by 1. And you'll see that, you know, it's a good step. I do it all the time, right? Where I just keep bounding it by 1 whenever I have this term, which can go off to be unbounded. Now, once you do that, it tells you that your now domain, so from here, so from this definition, basically lives, okay, somewhere within here, okay, between 0 and 2. And on that, so on this particular kind of restriction, okay, on that domain, you can now restrict this. So this can now be restricted. So you can say that this is now less than, and you can pick now what value of x inside of this, okay, or on the boundaries will make that term the largest. And as you can see here, 2 is going to make it the largest. So what you would have is, so you can now put in, so 2 will be squared. So that would be 4, and then 4 plus the 2. So you're going to be bounding it by 6. And this is what you will have. So what that means right here, so this is 6, and then x minus 1. So on this restriction, so based on this restriction, when we're living, okay, on this particular domain, we know that we're always going to be restricted by this. And now from here, you can now obtain your delta, because what you want ultimately is you want this entire thing, which you started off with, so this right here, right, to be less than or equal to that, which ultimately is supposed to be less than epsilon, right? So this is supposed to be epsilon, less than epsilon. So as you're now setting this up, so you can just say, all right, so this is less than epsilon, and now hopefully you can clearly see, so this would be epsilon over 6. So here's our bound, that's our, you know, C, okay, so we've set it up to 6, and now we have to check if this actually works, right? Now our delta, so as you're defining delta, okay, so delta is going to be equal to, because we have restricted, okay, this to live within 1, so notice that it's going to be either x minus 1, which is going to be less than epsilon over 6. It's going to be, you know, one or the other, right? So we can choose whichever one is the minimum. Now, if we are, you know, within this particular, okay, domain in here, we know that this will work, right? But what we have to do, because we've restricted it, we have to say, all right, so take the minimum, right? Epsilon over 6. And taking the minimum always will hopefully work for us, all right? So now we want to be able to see if this indeed will work. So now you're going to be jumping into step number 2. So that's the step number 2. Now we actually have to show that the found delta actually works. So does it actually satisfy? So if we are indeed bounded within here, so for us, so this would have been right here, so this is x minus 1 is less than delta, and now delta has been defined in this way, then what we know is that, our function, okay, minus the limit, so that means that our function, which is x cubed minus x minus the limit, which is just 0, this is supposed to be less than epsilon, right? But, well, what do we know? Well, we know that this is equal to, so we had x squared, right, plus x, and this is x minus 1. So that we've already done, so we're kind of going back in reverse. We know that this is true. And now we know that all of this, okay, so this is now 6 is definitely bigger than that. And we know that this, okay, within our bound, okay, within that 1, we know that it is the minimum of that 1 in epsilon over 6. Okay, so we know that this would be our within our delta, so this would have been epsilon over 6. And notice the 6 and the 6 will cancel off, and therefore, so this is equal to epsilon, which shows exactly what we wanted. So that means that this is going to be indeed less than epsilon if you are within this bound, all right? And that's exactly what we wanted to see. So that's your delta. All right, so let's now take a look and see. So let's put up decimals. Let's take in this function itself and see how this limit will work visually. So on the actual decimals that you see there, so notice I put in the function here. My a is equal to 1 because x is approaching 1. My c is actually that bound, all right, which I've called c. So now we said that this was going to be 6. So I'm going to set it equal to 6 right there. And now, so that means, notice that our delta is going to be the minimum between 1 and epsilon over 6, all right? And then epsilon is right below here, and then the rest is just kind of drawing everything out. So let's see, what happens and how this looks like. So that's our cubic function, so that, should be familiar to you from high school. And then if you're going in, okay, so we have to now zoom in because we're going on, okay, right there. And let's see what happens. Okay, so there you go. So that's our kind of conservative range on the actual delta that we have. Here's example number 2, and this one is a little bit more complicated and involved, and let's see, how we would approach this. Now, I'm not going to go through, every single step. The hardest part is, of course, finding the delta, so I just want to be able to show you how you can do that, and I'll do that for all the remaining examples so that the video doesn't take up too much time. But of course, don't forget that you do have to do this kind of final step in showing that your delta that you found actually works. So here, as you're coming in, so this is our new function right there. So let's write it out. So we're going to get 2, this is x cubed plus x squared minus 4. The limit, so this is minus the limit, which is going to be 16. So now, again, we want to be able to find a connection, and our connection is supposed to be, this is supposed to be in some way bounded by some, constant, multiplying x minus 2. That's ultimately what we want to do, is because we want to find our delta. So now let's take a look. So I'm going to break this down right here. Now when I say equals, okay, I'm referring to the one which is right above there. So we'll have 2, this is x cubed plus x squared, this is minus 20. So that's what we have. Now you're going to have, as the functions, when it was linear, very easy. When it's quadratic, factoring quadratics is also not that difficult. When you have now a cubic, it's not always the easiest thing. But again, keep in mind that you do know, all right, and you can just double check, making sure that the limit actually is correct. Okay, you do know that this is going to be a factor of this, right? So you do know that. How do you know that? You can just use your remainder theorem. So you can just substitute 2. When you substitute 2 in here, notice what you're going to get. 2, this is 8, plus 4, minus 20, right, which is 16 plus 4, so this is equals to 0. Now this shouldn't be a surprise because it is a cubic, it's a polynomial, so it's very well defined. So you know that this indeed should be a factor if this limit would have held anyways. So now if you know that that is true, now factoring, it's still not going to be easy, but you can go back to any method that you like. So for instance, you can use long division, so within here, so I'm going to put 2x3 plus x squared. I like to put this 0x when it's missing a term, and then minus 20. And now you have to go back to doing this, okay, kind of the long division. So if you've forgotten that, I'll put up a link up above there. You can go through it, and then I'll just do this kind of in fast forward motion because it's a high school component that probably you're just going to have to just refresh yourself on. So that's what we get, all right? So I went through this whole process, and therefore, so we're coming up, okay, with this. This is the connection that we really wanted, and this right here, what you have right there, that is what you want to put a bound on, all right? So now this is a quadratic. You might think like, do I still have to factor this? No, you don't have to factor it at all. You just want it to be able to obtain this actual term by something else, by another factor, and now we want to put a bound on this. Now again, if you don't put a bound on x, okay, in your original, so around your kind of limit that you're approaching, so this is going to be x, minus 2, so you have to put a bound on this in some way. So I'm going to, again, just as I normally do, I'll just say, okay, let's just live where this is the case, and again, I just keep kind of reminding you that what this means is, on the x, we can't have x going to infinity because this whole thing is going to blow up on us. So there would be no bound, right? So we wouldn't be able to finish our epsilon-delta proof. So we need to kind of restrict ourselves to be within some bound. And I'm just restricting a bound that basically lives, okay, 1 away from 2. So that's what I'm trying to do. And now within this, now what you want to do is for every single x within this, okay, as it's bounded, you want to find the largest value, okay, for this, right? Where would this be the biggest value, right? So that it bounds the entire thing. So this would have been now less than, and then the largest thing, I guess, would have been the 3. So if we substitute the 3 back in here, then this is what we're going to get. So that's what we get unless I made some numerical error. So now we have our C, right? So this is the bound that we wanted. So we know that within this whole restriction, okay, that we put in, 43 will work, right? So it's going to bound this entire thing. So now, so this is supposed to be less than epsilon, which means that x minus 2, so we can set epsilon and then divide both sides, and you found your delta. So your delta is always, this is going to be true for pretty much all the polynomials that you do whenever you're trying to fix a bound. So I picked 1, and then you get epsilon over 43. Now I encourage you when you practice this, you don't have to stick this to 1, although your profs probably will do that. This is the most common thing that I have seen. You can restrict it to 2, to 3. You can be more conservative, or you can be less conservative and just restrict yourself that, all right, well, we don't, since we're finding a limit, we don't have to go 1 away. Really, we're trying to approach 2. So, you can set it to be less than 0.5 or less than 0.1 even, and it will give you a better approximation for the delta, within that bound. Okay, so that's what you would have in there. So there you have it. Okay, so that's what you would see. Now let's see this visually. So if we take out decimals, all right, so I'm going to just update this just so that you can also see how the code works. So this is 2x cubed plus x squared minus 4. That's my function. I am approaching 2. In this case, my bound that I found was 43. All right, so 43 right there. And, so now we can go ahead and play around with this. Okay, so let's see. I got to zoom this out. All right, so there you have it. So I had to kind of zoom it in just so that we can see it. So the blue ones, so that's basically where the delta is, right? So if you're restricted within there, you want to see if you're within your function, within your epsilon, and indeed that is the case, right? So if you were not within it, then that means that the blue would actually overlap further, and then there would be values that you would find where go beyond epsilon, away from the limit. And of course you can make this bigger, just to play around and see how it adjusts. Now delta is in terms of epsilon, right? So it's basically a function of epsilon, so it just adjusts it, okay, as needed. So as you make this big, it makes it big. If you make it small, then it narrows in, and then you would have to zoom in a little bit more in here. Here's the next example, and again, it looks even harder than the previous ones. Now this one is actually in its form. If you remember transformations from high school, you may recall that you can shift around. You have a parent function, so this is a cubic function, okay, so it has a parent, okay, and then you can just shift around, up, down. You can do kind of translations back and forth. You can compress it, okay, and so on. So within here, we can tell quite a lot of information from this, okay, if you still remember your transformations. But you notice that this isn't in our standard cubic form, right? So this is going to be a little bit annoying, because we're going to have to do a little bit of distribution, but that's fine, all right? So hopefully you still remember that. So let's find our delta. So, how would we proceed? Well, first of all, I'm going to, so if I take this, oh, and by the way, so, I just started this. You can certainly use the binomial theorem, okay, if you wanted to, and if you still remember it. I'll put up a link up above there, because if you, so on the cubic side, sure, you can do this, what I'm doing, but I just caught myself. You can certainly just go ahead and find the values and coefficients through the binomial theorem. All right, so I'll just pause in here, and I purposely have done this just so that kind of hopefully rings a little bit of a bell for you from high school, from that binomial theorem distribution that you can use. All right, so now once I have this, I'm going to literally just kind of fully out, expand, and then I am going to, okay, so take this, so meaning this is what I'm going to do. This is my f of x, right? So this is all of that minus and minus 189, which is my limit. So that's what I want to do is, so let me just expand the whole thing out. All right, so here you go. All right, so that's how it would look like. So we have all of this. I took out the -3, so this really will just be 3, the absolute value. And now what we want to do is we want to now take this, and again, so what we're looking for is we want to try to make the connection. Okay, so this is approaching -2, and we want to put a bound, right? So we need some c in here, and now that c is, so I guess that c is, well, let's put maybe c bar, okay, because the total c will be 3 times this, okay, because there's a 3 in front there. So, that's the next step that we want to be able to do. So now you can again just double check for yourself, all right, did I do everything correctly? And then just play the game of just saying, okay, let me substitute 2 in there because I want to see if this indeed is still a factor, right? Because otherwise maybe I've made some kind of a arithmetic error. And you should also probably substitute 2 in here before you're even starting to see if this is indeed 189. Because then it wouldn't have been the limit, right? So let's take a look in here. So I'm going to do it in fast forward fashion. Okay, I'm going to factor out the x minus 2, and then we'll have a remainder polynomial, which is going to be some kind of a quadratic, which we're going to be putting a bound on. So there you go. So it's fully factored now. So this is what we wanted. We wanted this connection. We have this 3 in front, and we want to put a bound on this. So how do we put a bound on it? Well, we have to restrict, okay, within how are we going to be living, okay, in which range or which domain. So again, so I'll just stick this and make it simple, okay, so put it less than 1 so that we put a bound on this entire thing. So now with this, so notice that they're all positive. Okay, so within here, so around 2, we can go to 3, and then this will go to 1. So within here, I guess 3 is going to be the value of x that is going to make this entire thing the largest. So this whole thing is going to be less than. Okay, so this is 3, and then we have to substitute 3 in here. So what is that going to give us? 9. And there you have it. All right, so that is your C. Okay, so it's rather large actually in comparison to the other examples. And what this would mean that your delta, so you can let delta equal to the minimum, so whichever one is smaller. Remember, if a delta works, then anything which is smaller than that delta will also work. Just make it more conservative, and that's okay. There's going to be epsilon over 183. And let's take a look. Okay, let's pop up decimals and let's see how this one looks like. All right, so let's change this up. So this was -3, you know, x plus 2, this is cube, okay, plus 3. And we're gonna, our 2, okay, so that's approaching 2 as well. Our C is, we found to be 183. So we had 183. And there you have it. All right, so let me zoom out and zoom in and find this. All right, so here it is. Okay, so we're going all the way, notice at 2, and then -189. So I got to zoom in there. And look at that, that's wicked. Okay, so it's amazing. So notice within our delta, right? So we're within that bound, and we are indeed within our epsilon of the limit. Okay, and you know, so you can make this a little bit. If I make it bigger, I would have to zoom out. Let me zoom out, I guess. Okay, so I'll make it a little bit bigger, and notice that the delta changes beautifully, right? So that we're still within, so within that range of the domain. Okay, we are indeed stuck under that epsilon, which is what that epsilon-delta proof is all about. And then if you keep zooming back in, all right, so if you make epsilon smaller, look at that, beautiful. Okay, so that works as well. So here's the final example. This is actually just a generalization. So this most likely, I don't know, maybe your profs will be mean to you. Now they'll give this to you, but I have generalized the linear one, I've generalized the quadratic one, so we can certainly generalize the cubic one. And I hope that you can see that if you had now polynomials which are larger, right? So to the power of 4, so 4th degree, 5th degree, 6th degree, you would go through exactly the same process. So it always will be, you know, trying to figure out factor out, okay, your x minus a, and then what you want to do is you put a bound, right, on whatever factor is remaining, and then, you know, the trick that you play is, okay, you say, well, if it's unbounded, we're going to set it less than 1, and then we're going to find the largest value. And that's here because we don't know what capital A is, we don't even know what small a, what b, etc. What these are. Now we'll assume that, let's say, capital A is non-zero, because if it was, then it's back to the quadratic case, and we've done that already in the previous video. But in here, let's take a look at this. So I'm going to start it off. All I'm interested in, again, is finding the delta, and I just want to show you that this isn't that bad. So that, you know, what would we do? So we have to take absolute value. Okay, absolute value, absolute value. Okay, so now let's actually do this. And if you do end up collecting these, so notice this one and this one can be collected. So that's going to be, and then the d's, you know, fall off. Okay, so those constants are gone. So that's what you would have. Notice that we want a connection with x minus a, and there's an x minus a in all of these. So in fact, so if you look at this, okay, want to recall this component, right? So all the, I think I've even done an nth order one, but I'll put up a link up above there. So if you've forgotten, okay, these nth differences. And then, you know, you have your a right here. So that's that first term. That second term is going to be b. Again, x minus a, this one's easier because this is a difference of squares, which you're probably more familiar with. So that's what you're going to have there. And then your last term already has the x minus a. So the only thing that I wanted to highlight is you have this in every term. So we can factor that out, and what you're going to be left with is this. that's what you will have. And so now, so from here, we have to put a bound on this entire thing, right? So that's exactly what we want to be able to do. So how are we going to put a bound on this? So we have to bound x. So within here, so how would you continue your proof? You would say, all right, well, we are around a, and we're going to bound this by 1. So meaning x minus a bounded by 1, which would mean this is a plus 1 and a minus 1. We don't know what a is, if it's positive or negative. It doesn't matter. And now, so on this particular kind of fixed domain that we have, how can we now bound the entire thing, right? The constants, those are simple. However, the x, because we don't know if a is positive or negative, we don't know if this is going to work or this is going to work. So we kind of have to take the largest one possible and make it positive. So in that instant, okay, so what it will be this, a plus 1. So we can bound the a plus 1. We know that this is positive, and it certainly will be bigger than any value, okay, that we have within here. And therefore we can substitute it now into x, okay, everywhere, right there. So that's what I'm going to do. Now, when I substitute it in, I will have to now go through the annoying process of, kind of massaging it out, collecting like terms, etc. So let's do that and see what it gives us. All right. Okay. So, all right. So I collected everything out. So basically, this is what your C will be. All right. So this whole thing. So call this little c, not the capital C that we had in there, and that little c will basically be like this, right? And then you want to make it so epsilon over c, and then your delta would have been the minimum, okay, of that 1, or the epsilon over c, where the c is all that junk, okay, this right here. Now what I want to just point out to you, because I hope that you can now see the pattern, especially if you've watched the other videos on linear and quadratic, is that notice if this a was 0, just dealing with the quadratic case, and you would have gotten this. And if you go back to that video, you'll notice that, oh, okay, yeah, it's the same constant. And then if b and a were 0, now you're back to the linear case, where you would have just had this, which really was just your slope, right? So your c was just the magnitude of your slope, and that indeed was that case. So there you have it. You can certainly generalize this to any polynomial that you like. You can now find your deltas, and I hope that through this series, which are lengthy videos, but hopefully now you can say like, all right, I'm confident in these. Okay, so I'll do more epsilon deltas. We'll tackle the parent function of absolutes, and then see what trick do you need there. Okay, thanks for watching. We'll see you in the future epsilon deltas. Bye everybody.